Okay, so very good morning to all of you.
Morning, ma'am.
Yeah, so I think there are 17 people. Okay, so yeah, as always, any concerns, and it's an early morning, but yeah, any concerns other than that with the course and how do you find it? Have things been okay?
All good, ma'am.
All good. Okay. So, just a reminder about your assignment. So, your first assignment is due exactly in a week from now, from today. So, I hope you guys have all started, and I hope you're enjoying the assignment. So, sometime I'll also post the next assignment too. I'll try to post it a little, sooner than next week. So this will be based on whatever we are doing now, and maybe in the next few classes too. Okay. So that was just the heads up. So let's begin today's class. Okay. So I hope the screen is visible.
Yes, ma'am.
Okay. Cool. So remember, we were learning iterative optimization techniques, and we looked at some gradient-based methods. So specifically, we looked at this method called Steepest Descent, where what you do is at every step of the iteration, you compute a new point by so xk plus 1. You do it by taking the previous point, and then you add a quantity which depends on the gradient. Okay, so gradient at the point xk. So this was the kind of update. So the direction was negative of the gradient at xk, and there was this alpha component. Okay. Now we also saw different ways in which you can choose alpha. So maybe let me just open that one so that it's a good recap for all. Okay, so for the directions, like the direction you go, the descent direction, we saw that these were some options you could use. So negative gradient, and that is what we call steepest descent. Then we had this Newton direction where you take the Hessian at the point xk, you do an inverse, and then you basically scale the negative gradient by this quantity. Okay, it's a translation of the gradient by this quantity, this matrix rather. Okay, and then we saw different such variants, right? And for the step size, we saw something called an exact line search, where you choose the alpha, the amount by which you move, to minimize this quantity, so the function value at the next step. Okay, and there were some other options you could use, like constant step size, and choose alpha k as 1 by k, and so on. Okay, so today I'll just show you an application to that of whatever we saw last time. Particularly, we'll take the steepest descent method and we'll apply it to quadratic functions. So basically functions of this form. Okay, so f of x is half x transpose qx minus b transpose x. So we had also seen this earlier in the context of writing the necessary and sufficient conditions. Okay, so now we'll assume that this matrix Q, so we assume that that's positive definite. Okay, so the reason being that if it's not positive definite, then this problem can become unbounded. Okay, so in the sense, like, you remember that a matrix is positive definite if all its eigenvalues are positive, right? So suppose it has a negative value, then this f of x can become unbounded. So do you any guesses why, or do you have an understanding why this could be so? So Q has a negative eigenvalue, which means that you can have some vector y such that Qy is lambda y, and this lambda is negative. Okay, so then you can have f of x can be unbounded.
So f of x will become negative for some value and then it will just keep getting more and more negative. My
Exactly.
guess.
So yeah, that's exactly what can happen. So if you take your x as this eigenvector y, Okay, so then what happens is you can keep making y larger and larger, right? So if y is an eigenvector, then even the scaled value, so if you multiply y by some beta y, that also becomes an eigenvector. Okay, so you can keep on doing this, and this quantity is going to become arbitrarily small. Okay, so that's exactly the reason why if q is if I mean we require q to be positive definite. Okay, so now another thing is if q is positive definite, it's also, this problem is also going to have a unique global optimum. So we will see this later, of a couple of days later when we do convexity. So basically this function is convex if this matrix q is positive definite, and such problems have a unique global optimum, and all the local optima are also global optima. Okay, so yeah, just something to keep in mind, and maybe you want to come back to it later once we do convex functions. Okay, so now let's apply steepest descent to this problem. So recall that what we needed was the was the gradient first. So for this function, the gradient is, we have done this earlier. It's just qx minus b. Okay, so the update is going to be of this form. Xk plus 1 is xk minus alpha k times qxk minus b. Okay, so now how do we set alpha, right? We want alpha to minimize this f of xk plus 1. Okay, so what you can do, let's just see how we do this. How do we minimize? So this is also a minimization problem in turn. So let's just write this. So f of xk plus 1 is going to be what? It's half, I mean, that form, right? So it's half xk plus 1 transpose q xk plus 1 minus b transpose xk plus 1, right? So that's the form we considered. So this form, so I'm just going to substitute the values of xk plus 1. Okay, so yeah, so this is just going to be half xk minus alpha k q xk, or let me just call it grad fk for now so that it's not very cluttered. So xk minus alpha, I'll just call it alpha, say grad fk. Okay, so I'm saying that grad fk is a shorthand for, it's just gradient of f at xk. Okay, so this is going to be a little bit of algebra, but let's anyway do it so that things get clear. Okay, so this is xk plus 1. So I'm just going to do this multiplication. So again, q times xk plus 1. So that's going to be q xk minus alpha q delta fk. Okay, and minus b transpose, so xk, instead of xk plus 1, I'm going to substitute this. So b transpose xk minus b transpose delta fk. Okay, so times alpha. Okay, so please stop me if you spot some mistakes. It's very possible that I mess up. Okay, so now just expanding this, can someone tell me?
qxk square.
Yeah, so this is a vector, and so in terms of vectors, we don't call it square, right? So all xk, xk plus 1b, all these are vectors, right? So you would call it xk transpose qxk, right? So half of this. Okay, so that's something, just keep it in mind whenever you're doing these operations. You have to specifically note whether it's a vector or it's scalar. Okay, so xk transpose qxk. Then what else
Uh,
do we have?
Plus alpha square grad fk q grad fk.
Yeah, plus alpha square grad
Grad
fk,
fk transpose.
grad fk transpose q grad fk, and
And then
then
xk
we have something else, right?
transpose minus alpha xk transpose q grad fk.
Xk transpose q grad fk. Is that all? Fk.
No,
So minus half
minus
and half
alpha.
half,
Yes,
right? So
minus
that
alpha. This also
go.
minus alpha grad fk transpose qxk.
Okay. Fk transpose qxk. Okay, fine. Let's write this, and that is the first quadratic term. Then what do we have here? This part is just minus b transpose xk
Plus
plus alpha b transpose grad fk, right?
ma'am,
Okay.
the way we got the second equation, basically f x k plus 1 equal to something, then how we got that this grad fk part, that was that done in a previous class? I think I missed that class.
No, I don't know if I got your question. So fxk plus 1, this I'm just plugging in the quadratic function. Okay, so that is fine, right?
How did we write that grad fk or that xk minus alpha grad fk? How did we get
Okay.
this from?
Yes, so this is the steepest descent update. So at every step, at every iteration, you compute xk plus 1 as xk minus some alpha times grad fk.
Okay.
Okay, because
Oh,
we
okay, yeah, it's
remember,
written.
yeah, we looked at these descent directions, right? And we showed that, if you go along the direction of the negative gradient, that
Yes,
is
ma'am.
going to give you a descent, right?
Yes, ma'am.
So we are particularly using that update where you go in the direction of the negative gradient. Okay, so yeah, thanks for asking. I hope, I'm sure many others would also have had this question. I hope it's clear.
Okay,
Uh,
ma'am.
okay, so yeah, so this is what we have. Now let's just do some more simplifications. So one thing is these terms, right? Uh, these two are actually going to be the same term. Okay, so this is just going to be a scalar, right? And if you take the transpose of this, you're going to get this. So it's just a single number, and in terms of transpose, you can represent it either in this way or this way. Okay, so this is just going to be half xk transpose qxk plus half alpha square grad fk transpose q grad fk minus, so there's a two factor coming in here, and that cancels out with the half, so it's just going to be minus alpha xk transpose q grad fk. Okay, and then you have a minus b transpose xk and also a plus alpha b transpose grad fk. So I'm just writing it this way so that I want to bring it in one form. So now you see this fxk plus 1, what we've done is we've written it in terms of the alphas. So everything else at this point we have xk and we have grad fk. The only thing we don't know is alpha. Okay, so this is a problem of the form. So let me just again write it, group the terms so that things become a little more clear. So this is one term. So these are basically constants which don't involve alpha. Then there is a term which involves alpha alone. So this is B transpose grad Fk minus Xk transpose Q grad Fk. Okay. And there is an alpha square by 2 term. And for this, the alpha square term and this coefficient is grad Fk transpose Q grad Fk. Okay. So now if I view this as a function of alpha, so this will be something of this form. Okay, G alpha is say some C plus B alpha plus A alpha squared. Okay, so this is a quadratic in alpha. So why I'm writing it as a function of alpha is just because this is the variable, this is right now what I want to find. Everything else is fixed for me. Okay, and now I'm trying to find an alpha which will minimize this quadratic term. Okay, and in particular, one thing to note is that A is greater than 0 here. Why? Because Q is positive definite. Okay, and so this term, which is the equivalent of A, and that is going to be greater than 0 for any value of grad fk. Okay, so So now how will you minimize this G alpha? What is the alpha which minimizes this? So remember we did some things, right? The necessary and sufficient conditions.
Set the
So
first
how?
order differential to 0.
Yes. So G dash alpha, you set it to 0. So what would that be?
2 alpha A plus B.
Yeah, B plus 2A alpha, so that is 0. So you get alpha is minus B by 2A, right? So,
That's right.
right. So this is okay. So this is a critical point. Now, if you take the second derivative with respect to alpha, so I write it as G double prime because it's just a single number alpha. If you had a vector, you would have to write it as a Hessian. It would be this would have been a matrix. Okay, so G, the second derivative is just going to be the
2.
derivative of this, right? So, right, it's 2A. Okay, and here A is greater than 0. So that's why you have this alpha that you compute here is indeed a minimum.
Minima.
It's a minimum point. Okay, so now coming to this problem, so let's just substitute what the B and A's look like here. Okay, so alpha is going to be what? So minus B transpose grad Fk. Okay, minus, okay, so minus B transpose grad Fk. So I'm just putting in, this is the value. Okay, so I think there's a thing here between this B and this B. So these are different, okay? So maybe let's just make it a different thing so that it's clear. Okay, so I'll just call this Q. Okay, I don't know if anybody got confused because of this, but anyway, let's just keep it this way. So now, so this Q is the coefficient of the alpha terms. So that is just this one, right? So what would that be? So negative of Q. So that is just minus B transpose grad Fk plus Xk transpose Q grad Fk. Okay, is this clear? I'm just
Yes.
substituting this value here and 2A, right? So A is actually A is half of grad Fk transpose Q grad Fk. So 2A is grad Fk transpose Q grad Fk. Okay. Now there's something more you can do here. So here if you see, this is just minus B plus Q, QXK transpose grad Fk. So the numerator, I'm just taking the grad Fk as common and the denominator is just the same. Okay. So, okay. So now what is this term here? Qxk minus B. This is something we already computed, right? So this is the gradient. So gradient evaluated at xk is Qxk minus B. So that's why what you'll get here is grad Fk transpose grad Fk by grad Fk transpose Q grad Fk. Okay, so this is the optimum alpha that you will use at every step. Okay, so is this thing clear? Are the steps and all clear?
And why will it not be minus B plus Q transpose XK? Is Q a symmetric matrix?
Yeah,
Oh,
Q
yes,
is
it
a
is a
symmetric.
Hessian.
It's a Hessian, and we take it as a symmetric matrix
Yes,
here.
yes. Yeah.
Okay. Yeah. So anyway, yeah, what you said is right. Ideally, it should have been a Q transpose, but yeah. Okay, so is this clear to all? Are there
Yes,
any
ma'am.
questions? Yes, Rohit, this clear. So please type in the chat box or respond if things are clear.
Ma'am, by saying boundedness, do you mean upper bound or lower bound? Q you said in the starting.
Yeah, so here we are looking at a minimum. So what we mean is the lower bound,
Okay.
right?
Yes, ma'am.
Yeah, that's a good point. So if you're looking at the upper bound, so that by the same logic, if it is positive definite, the upper bound can be quite large, right? That can grow arbitrarily large for a positive definite matrix. Right? Yeah. So are these steps clear? What about the others? I don't hear from the rest of you. It's clear. Debiani says it's clear. Okay, it's clear. Okay. Okay. All right. Okay, that's good then. So let's now just see an example. Okay, so if, we took in particular quadratic function here. Now, why quadratic? Because this is going to show up in many places. So, for example, in your several of these machine learning applications, you will have some kind of a loss term which you want to minimize. And many a time, these loss terms that you take are of the form, they are of the quadratic, the functions are quadratic. So that's why this, I've specifically taken this quadratic example. You'll also see perhaps in your next assignment, how you could use it in the context of maybe regression or, some other machine learning applications. I'll try to make you get some practice for that. So let's just see now we've derived all these steps. Okay, let's just see how you would apply it in a numerical example. So here, this is a function I'm going to take. Minimize 5x1 square plus x2 square, 4x1 x2 minus 6x1 minus 4x2 plus 50. So this is a function which is quadratic. So it's in 2 dimensions. So this function is from R2 to R. Okay, so x1 and x2 are the variables here. And so first, let's just try to bring it in this form, okay, of this form that we saw, half x transpose qx minus b transpose x. So can you tell me what the q would be? So q is going to be a matrix, right? It's a 2 cross 2 matrix. So any guesses what q would be? Okay, so when you write something like, let me just explain this a little bit if things are unclear. So when you write something like, okay, so you have 10 here. So this is going to be a matrix. I will anyway explain it once we have written it down. So 10 then.
The bottom right is 2.
Okay. What about these?
Any one of these could be 8 and the other would be 0.
Okay, so we want it as a symmetric form.
Okay, so it would be 4, 4.
4, 4. Okay. So how did we get this? So who answered? Was it?
Ma'am, it was me.
Siddharth, okay. So can you explain how you computed this?
Yes, ma'am. Ma'am, I just observed that first x is multiplied with q, so we will get like, ma'am, I just actually went through the entire calculation.
Okay, fine. So let me just make it a little more like if there are people who don't understand this. So when you say a quadratic like this, right, half x transpose qx. So this is actually, it's just, so this term, if you take x transpose qx, it's just, okay, let me just leave out the half. Okay, so this is just going to be qij xi xj. That's just what this means. Okay. So now since we are saying, so you see that, if you take xi square, right? So whatever coefficient comes there, that has to be the qii. Okay, so if you take x1 square, the coefficient that comes there, that will be q11. Okay, if you're writing it in this way. Okay, and similarly, if you take, so this will be for x1 square. And if you take q22, that will be for x2 square. And now if you take x1, x2, it will have one of these terms, q12 and also q21. So you want those to be symmetric. So that's why these two terms will together give you the coefficients of x1, x2. Okay, now in particular, we have this half here. Okay, in all our things, we'll have this half. It's nothing, it's just because when we take the gradient, we want to, we don't want to keep fractions. We don't like fractions. So that's why the half is always there. Okay, so now, so what happens is q11. So, so you have to adjust these q's accordingly. Okay, so x1 square, if you take, that is going to be given by half q11. So when you write q, it should be 2 times the coefficient of x1 square. So that's why this 10 comes. So similarly, q22 is, half q22 is what will give you the coefficient of x2 square. So here that's 1. So, that's where you get a 2 here. Okay, and similarly in the other case, so x1, x2, the coefficient is 4. Now here there are these two terms, so half of this and half of this. So you just divide it between these two, so 4 and 4. Okay, so that's how you construct this matrix Q. Okay, now there's also this constant here. So actually for these function that we considered here, we didn't take the constant, but really that doesn't matter. So you can, it's general, you can put a constant here too. Okay, so all these calculations will go through because alphas won't change. So you can verify that later. But anyway, so let's take this. So Q is this. And so can you tell me what is gradient of F? So take the gradient with respect to this function. What is it going to be? So you know this, right?
10x1 plus 4x2 minus 6.
10x1 plus 4x2 minus 6. Okay, and?
2x2 plus 4x1 minus 4.
Minus 4. Okay. So I'm just writing down whatever you need to, implement the steepest descent algorithm. Okay, so now the gradient is done. So now the Hessian, what is the Hessian? It's just Q, right? So that's for these quadratic functions, that's what the Hessian is. Okay, so so what to implement this, what we just need to do is we have to compute these updates. So alpha, so you have the gradient now. So alpha you have already computed, which is this. Okay, so you just need to do these computations, and the direction is just going to be the negative of this gradient at every point. Okay, so let's just do that. I've already done an implementation, so I'll just quickly show that to you. Okay, so yeah, I hope the code is visible too. Is it big enough? Yeah, okay. Okay, so here this is all some things that I've just done to plot the contours and things like that. So the most important thing is this is where you set the starting point. Okay, so I'm just starting from this point -4, 8. So it's just an arbitrary starting point I chose. And this is the Q. Okay, this is what we had. And the B is this, right? So that was also something. So B was the coefficient of the linear terms. So it's just, so B is -6, -4. Okay. So yeah, so that's what we have here. And okay, so these are all just for enabling plots and making it look nice. And so here I've also computed the gradients. So this is just what we did. And so ideally you would write all of these as separate functions, but I've just done it this way to quickly be able to show you. And the gradient computation was this, and this is the gradient descent update. Okay, so Gx is the gradient, and this is what we just found out. We just computed this and multiply this with the gradient negative of this. So x at every step, you're just doing x is x minus this. And I'm going on, and my stopping criteria is, as long as the norm of the gradient is greater than or equal to epsilon, I keep doing this. Once it is below some epsilon, and that epsilon is a very small value, so once it's below that, I'm going to terminate. Okay, so let's just run this. I'm also plotting the contours and showing you how the steps look like. So I'll just do that once. Okay, so it's taken me 17 iterations. Okay, I started with -4, 8. Okay, and in the next step, the point I got was this -2, 8. And then it kept updating in this way, and total of 17 iterations it took. And if is this plot visible to you?
Yes, ma'am.
Okay. So this here, what I've shown is the contours. So this is the x1 and this is the x2 plane. And, this is the point from where I started. So this was something like -4, 8. Okay. And this is the path. So in the next step, I went along this direction by using steepest descent, and I came till here. So initially the objective value was 23, and then it dropped to around 13.7. Okay. Now the next step, it went a little more further, and then the objective reduced. It became 11, and so on. This step, went on for about 17 iterations. Okay. So this is the trajectory of steepest descent. Now, one feature of steepest descent is that, the subsequent directions. So this is the first direction, and after that you went in this way. Okay. So one feature here is that, the steps, the directions are always going to be orthogonal. So in one step, if I go like this is the first direction, and the next one is going to be orthogonal to the direction I took earlier, and so on. So this one is orthogonal to this, and so on. That's a feature of steepest descent. Okay, so and that is kind of showing up here in these contours. Okay, so I just wanted to show you this. It's a lot of theory sometimes just gets overkill. So if you just see it happening, it's perhaps more interesting. Okay, so yeah, you will also get some practice by doing these kind of problems in your assignment, and you should also try this out yourself. Okay, so yeah, so I just mentioned to you about this orthogonality of the subsequent directions. Now you can also prove this. Okay, so the proof is actually, the idea is very simple. So suppose this is the sequence. Okay, x-case, x1, x0, x1, x2, and so on. And this is the sequence generated by steepest descent. Now the claim is that in every iteration, this direction xk plus 1 minus xk, and if you take xk plus 2 minus xk plus 1, okay, so this is going to be orthogonal to each other. Okay, so let's just see a proof for this. So remember how we computed these xk plus 1 and xk plus 2? So they were just computed in this way, right? Xk minus alpha k grad fk, and xk plus 1 minus alpha k plus 1 grad fk plus 1. Okay, so by trying to show orthogonality of these two, okay, what you're essentially trying to show is that the gradients, these two are orthogonal. Okay, because xk plus 1 minus xk is just a function of gradient at k, and so on. Okay, so now one thing that is important here, it's the way we've set the alpha that's also making a difference. Okay, so what we consider here is this function xk minus alpha grad fk, so f of that. So this is just xk plus 1, right? Okay, so f of xk plus 1 is just this, and as a function of alpha, this is what it was. And remember, we chose alpha to minimize phi k. Okay, so in short, you want the necessary condition. So this derivative of phi k, the first derivative has to be 0. Okay, for whatever alpha that we chose. And so that is just an application of chain rule here. Okay, so this is a function of alpha. So to take the derivative, you just take derivative of f evaluated at this point, xk minus alpha grad fk, times this term, whatever is the coefficient of minus alpha. So it's negative of grad fk, and this dot product is 0. And that is just this one, and so that is 0. So now that's what we have, right? So xk minus alpha fk is xk minus alpha grad fk is just xk plus 1. And this one is just the gradient at that point. So that's grad fk plus 1 and minus grad fk. So these are orthogonal. Okay, so that it's kind of a simple proof, but it's a nice feature that you have, that you're moving in orthogonal directions, and that perhaps gives you some, it's not like you're moving in redundant steps. Okay, so yeah, so that's about steepest descent. So any questions till this point?
No, ma'am.
Okay.
Ma'am, I get.
Okay.
No, Siddharth, go ahead.
So I didn't get the intuition behind why they are like orthogonal, the subsequent steps.
Same question.
Okay. So it's just about, it's the particular way in which you have chosen the xk plus 1. So it's about the steps also, right? So you have gone very far enough. So you have chosen one direction, that is the gradient at fk, so the negative gradient. And with this direction, you've gone as far as you could. Okay, so that was how the alpha was set. So now the next time the next direction you take, you don't go along this way, you go on something which is orthogonal, because in this direction that you already had, you went to the extent possible. Okay, so now you want a completely different direction, which is, you want some new dimension. So remember, the span of the whole of Rn, that is given by these orthogonal bases, right? So one of the gradients has given you some information, and now you are going on an entirely different plane. So a reduction along a totally different direction. So that's why, that's in some sense this orthogonality. It's in some sense it's a desired feature. Yeah. So yeah, it's just the idea that it's coming because of these alphas, that because you're going to the extent that you could with one direction. Okay. So then you don't have to go back to that plane anymore. Right. So does it make sense?
Yes, ma'am.
Yes, ma'am.
Okay. So yeah. Okay. So so now we saw this one descent algorithm. So many times, here we saw that there were like many iterations that you went for. Okay, so there were about 17 iterations. Okay, so in general, what is this number? How does it perform for different functions? Okay, so that is something that people like to analyze when they propose optimization methods. So that's why we study something called the rates of convergence. Okay, so now that any iterative optimization algorithm is going to give you this kind of a sequence of points. Okay, and suppose the sequence converges to some x star. Okay, so ideally you want this x star to be a local optimum. So that is what is of interest in optimization. So now how fast does this convergence happen? Okay, so that is the question of interest. Okay, so now if you see, if you compare these two quantities, so let me just take something like xk minus x star. Okay, so norm of this, and xk plus 1 minus x star. Okay, so how do you compare these two, right? So this is in one iteration, I was at xk, and this was how far I was from x star, where I would eventually converge. Now in the next iteration, I went to xk plus 1. At that point, how far was I from x star? So that is this. So what is the relation between these two? Is it, which one is lesser? Can somebody say?
xk approaches x star.
Right.
The left one should be closer.
Plus 1 should be closer, right? So xk plus 1 should be closer to x star, right? So this is always, you're going to have this kind of a behavior, right? So at every iteration, at every k, So this was the kind of sequence you had: x0, x1, x2, and so on. Then you had xk, then you had xk plus 1, and again you went for a long duration, and finally this approached close to x star. Okay, so at every step you're coming closer and closer to x star, and so this is true. But now what we are trying to say is this all that we can say, or is there something more that we can say, or is there something, is it, how does it, how is the relation? So is it just this one, or can you say that this is less than xk minus x star square, or maybe some higher powers? So what is the kind of notion here? Okay, so that's what we are trying to capture. So in general, the convergence, you say it's of order p, and some factor gamma, which is greater than 0. So if there is some point at k naught of the sequence such that after this k naught, so k naught could be somewhere here, for instance, and after k naught, any step you take, in every iteration, you're going to have this. That is xk plus 1 minus x star is less than or equal to gamma times this, what you had in the previous step, power of that to p. Okay, so if p is 1 and gamma is 1, that is something which we already know. Okay, there is that's expected always if you're going to have a descent in every step. But this is something stronger if you have some other values of p, some larger values of p, and maybe something smaller than 1 if you have. So here this was 1, right? This coefficient was 1. If you had some smaller value here, then that is something more desirable. Okay, so in general, if p is large, so say if p is 2, so in the next step, what the distance that you have from x star, you are improving by a square of what you had in the previous step. Okay, so that is better. So if you became better by cube of what you had in the previous step, that was even better, right? So yeah, so this is kind of the idea behind these rates of convergence. So based on the values of p and gamma, there are different things. So linear convergence is when you still have this kind of a behavior, but instead of 1 here, you have something smaller, a factor of gamma, which is less than 1, strictly less than 1, and that's called linear convergence. Okay, so that's one thing. And sublinear convergence is what we already know. This one is sublinear convergence. Okay, and this should be true for every k, beyond some k naught. Now, quadratic convergence is even more desirable than linear. Okay, so quadratic is when you have some square here. Okay, so that's quadratic. And in general, superlinear is when this power p here is something greater than 1. And as p increases, that is more and more desirable. So your algorithm is faster and faster as p increases. Okay, so large value of p and a small value of gamma is what is desirable. Okay, so let's just see some examples of this. So for example, yeah.
This is true for k greater than or equal to k naught, right?
Yes,
after k steps, we can say that. So what about these previous k steps? Why can't we say a condition like that?
Yeah, so the reason, that's a really nice question. So the reason for this is, initially you might start off very far. Okay, so all these things make sense when this values are themselves small, right? So for example, like if you take this quadratic convergence, so suppose you have something like xk minus x star, this value is something like 0.1. Okay, so xk minus x star, suppose it's 0.1, this norm is 0.1. Okay, so then in the next step, what you're doing is, the square of this, so 0.1 square, so that's 0.01. So you are less than 0.01 times closer if gamma is 1. Okay, so this is typically going to happen like these kind of things, right? These smaller numbers, less than 1 for this distance from x star, that's going to happen only, after you reach many steps. Okay, so suppose you have xk minus x star is, in the initial stages, suppose something like, say it is 4. So xk minus x star, if it is 4. Okay, so now 4 square is 16. Okay, so xk plus 1 minus x star. So if you're less than 16, okay, that doesn't, it's not adding anything, right? Because, you were already far, and I mean, now if you don't even have a descent direction, maybe this can happen. You might end up even going far away. Okay, so that's why in the initial stages, you don't consider that. So the idea is, after many steps, you are somewhere close to X star. And once that happens, then, how fast is it? How fast can you get to X star after that is done? Okay, so that's why you have this, after some point K naught, you should have this. Of course, now if starting from the beginning itself, if you have this kind of a behavior, then it's fine. I mean, K naught is just 1, right? Starting from the first step itself, you have this behavior, then that, of course, that is desirable. But always that does not happen in practice. Okay? So that's why, you have at some K naught, only after some K naught this happens. Okay. So was that clear? Rajneesh, right?
Yes, ma'am.
Okay. All right. So, okay. So let's just see an example here. So suppose the sequence, if I'm going to consider something like this, okay, 1 by k, xk minus x star is by k. Okay, so this can happen even if you just take xk is 1 by k. Okay, so this would be this something like, 1 half, 1/4, and so on. That's how the function, 1 by 3, 1 by 4, and so on. Okay, so that's how it goes. And finally, it converges to 0, right? So x star is 0 here. So this norm is, this difference at every point is just 1 by k. Okay, so now if you take, so xk plus 1 minus x star, what are you going to get? It's just the same thing, right? So it's just 1 by k plus 1. Okay, so now if you take this ratio, okay, so you take this ratio with xk minus x star. Okay, so this is just going to be 1 by k here. So what is this? So this is 1 by k plus 1 by k. Okay, so what is the value? You can simplify this further, right? 1 plus 1 by k. Okay, so now as, so the idea is, so remember here is you should have some k naught such that this is true. So in some sense, it's actually the limit as, k tends to infinity. So that's what you are interested here. So now this limit as k tends to infinity, what is this value here?
1.
1, right? Okay, so so what you have here is now this, if you compare these two steps that you took here, so xk plus 1 minus x star norm. So this is always going to be less than xk minus x star. So what is going to happen is this gamma is a value, it is equal to 1 itself. Okay, so you can't put any number. So this gamma here, right? So this has to be 1. So if you put any number less than this, so gamma is 0.9 if you take, you're not going to have this, as k approaches infinity, because this has to be true for every k beyond some point. And at some point, this is not going to happen. So the only value of gamma is 1 here. Okay, so this is actually sublinear convergence. Okay. So is this clear how we computed this?
Yes, ma'am.
Okay. Okay, so now some other examples. So xk minus x star, if you have this as a power k, where a is less than 1, strictly less than 1. So then this ratio here, xk plus 1 minus x star by xk minus x star. Okay, this is going to be what? So this is a itself, right? A power k plus 1 by a, which is just a. And this is less than 1. Okay, so this is true always. So, and it's also true in the limit as k tends to infinity. Okay, so here what we have is this xk plus 1 minus x star. This is less than, so let me just write this, minus x star is less than a times xk minus x star. Okay, and so this is linear convergence because this A is also, it's strictly less than 1. Okay, so this is better than this convergence that we had here. Okay, so now another example is something like this, A power 2 power k. So let's take just the sequence. So something like this. So A, so then A power 2 power k, right? So k is 1, you have A square. Then you have something like A 2 power 2, so A power 4. Then you have A power 8, 2 power 3, right? Yeah, A power 16, something like this. And A is strictly less than 1. So suppose A is something like half, you'll get 1 by 4. If A is half, you get something like this, right? 1/4, then 1 by 16. So 2 power 8, right? So this is 256, right? Okay. So something like this. Okay. So this also converges to 0. Okay. So now this one, if you try to compute, so xk minus x star is A power 2 power k. So now the same ratio if you take. So here you can do something better. Okay. So you can say, so let's just write this. So this is A power 2 power k. And here this is, this is k plus 1. Okay, and this is A power 2 power k. So here this is just getting multiplied by A square, right? Okay, so you can actually go with a square here, okay, to get something better. So here if you take the square, what are you going to get? Something like this, right? So what does this simplify to? Any thoughts here?
A square by A2 power k.
A square by A2 power k, right? So this is going to be something less than 1 anyway. Okay, so anyway, so this is a lesser quantity. So what we have is, in this case, you have quadratic convergence. Okay, so this is
Why did we take a square now?
So if you took, so the idea is like you want to see how best you can do, right? So of course you can start with 1, and you, in this case also, you're going to get that, linear convergence is anyway true. Okay, but you want to see if you can do something better. So if you take 2, if you take P is 2 also, then it works. Okay, so even similarly,
3, 4, 5, any number.
Yeah, so you have to see in all those cases whether it's going to work or not. So in this case, it's going to stop at 2. At 3, 4, it's not, you're not going to have this kind of a relation. So that's something you can check it out. So it's the same thing even for these other problems. We stopped at 1 here, but if you, try for P equals 2, that's not going to hold. For example, here, if you take, this is not even going to hold for, the first example. It's not even going to hold for, when you fix a value of gamma less than 1. Okay, so it's not going to hold for, even powers. Okay, so that's the idea. So usually what you have to do is you have to, keep trying. If you get that this holds for, some power P, you try for even larger values of P and see if it holds. Okay, if it, at some point it's going to break, and that's what you declare as the rate of convergence or the order of convergence. Okay, so was that clear?
I'm still slightly confused about this topic, but I'll try this at home.
Yeah, so just I think the way to do this is, with practice. Just try some examples of some sequences and see what the rates of convergence, what you can get. Okay. So one thing you should remember is, if something is quadratic, if it satisfies quadratic convergence, it is also going to satisfy linear convergence. Okay. Because, as the square term, it comes, and these values are typically going to be very small. Okay, xk minus x star, something like 0.1, 0.01, because you're looking at later in the sequence. And so that is going to be less than xk minus x star. So this term is going to be greater than this always. So if you have quadratic convergence, then you also have linear convergence. That's going to be true. But the other way it's not. So you might have linear, but maybe that's all that you can do. Okay, so that's why this thing of, you need to, keep trying some. Once you get linear convergence, try also if you have quadratic or not. Okay, so I think this has been I've also gone a little fast, so it could be a bit confusing, but just try to work this out yourself, so it should get clear. So I think we are also running out of time. So I just wanted to quickly tell you about some results in steepest descent. I mean, we won't prove this. So I'll just take a few minutes more. If you have another class or some other commitments after this, you can go ahead, and the recordings are up. So so why did I talk of this rate of convergence? It's because, for all these algorithms, there's been some study, okay, of the rates of convergence. So for steepest descent, when you have this kind of quadratic functions, where in particular Q is positive definite, and if you do this exact line search, right? So that gives linear convergence. Okay, so and it converges to the global minimum. So this point is something we will see when we do convexity. Okay, so and also this is true if you start from any initial point. Irrespective of what initial point you start, you're going to get this kind of like linear convergence. Okay, and in particular, you're going to have this kind of a factor. Okay, so you remember this gamma was something we said, if it is small, then it is preferable. Okay, so this value of gamma here, it turns out it's something like this. So if Q, you compute the eigenvalues and you have a minimum and you have the maximum eigenvalue. Okay, so now the factor is something which depends on both of these. So lambda max minus lambda min by lambda max plus lambda min square of this. So what happens is if the eigenvalues are very close by, okay, so then this factor becomes very small, right? So this lambda max minus lambda min is a very small number. And so that is faster. So this gamma, so this is going to be the gamma value, and that is smaller. And so the overall algorithm will be fast for such quadratic functions. But now if this lambda max minus lambda min is very large, so something like, say, some 100 or something of that form, then this is also the square term. So that's also going to be huge. Okay, so then the algorithm can get very slow. Okay, so this is just some more insights about how the speed of steepest descent. Okay, and this is particularly for quadratic. Now, so this is for the case where you have a fixed, so the alpha that you chose was, we chose it so that, it's the best possible one. So then you get this kind of a behavior. Now you remember that alpha, you can also fix a value. Okay, you can, instead of doing this step of finding alpha at every point, you can just say, okay, I'm going to use alpha as, say, 0.1. Okay, so that's also another way people do. So now if you do that way, if you fix the step size in that way, then you will have global convergence. You will converge to the optimum only if this happens. So the alpha fixed should be such that it's less than this 2 by the max eigenvalue. Okay, so if you fix it in that way, then you will get global convergence. Okay, so I'm not going into the proof of these because I think it's a lot of algebra, and when I look at it, like, I don't know if I have some more ideas to convey in that. It's a whole lot of algebra. So if you are interested, of course, you can go through it. So all of these textbooks like Chong and Zach, Lowenberger, they all have these derivations. But I just want you to understand this kind of a behavior, that the importance that the eigenvalues play in determining the speed and the convergence results. So that's the idea I want you to carry with you. Okay, so any questions till now? I understand the convergence proofs can be a little you have to get some practice out of that. So do try. So other than that, is there are there any questions?
No, ma'am.
Okay. What about the others? Gardner is clear, okay. Devyani, all okay? No questions, okay. All right. Okay. All right. So, yeah, I think we'll stop here. So if there are any questions, I'll hang around here to solve any questions. But otherwise, yeah, thanks a lot for being here. Have a good day. I'll see you on Thursday.